Okay, welcome. All right, welcome everyone. And it's a pleasure to have Sarah Penington from BAT today, and she'll tell us about genealogy and spatial distribution of the Nparticle branching random walk with polynomial tails. And if you have any questions, please feel free to unmute yourself and ask your question, or you could also post your comment in the chat and I'll relate to the speaker. All right, Sarah.
Thank you very much. So thanks very much for the invitation to speak. So today I'm going to be talking about joint work with my colleague Matt Roberts, who's also at Bath, and our joint PhD student Jofia Taigash. So today I'm going to be talking about the Nparticle branching random walk. And this is an example of a branching selection system. So I wanted to just start by saying a little bit about branching selection systems in general. So branching selection systems are particle systems consisting of particles that can branch into multiple particles. So we think of that as them producing offspring. And they also move around in space in some way. And there's also some kind of killing rule that means that the total number of particles in the system is kept constant. So this first bit here is the branching part of branching selection system, and then this killing rule is the selection part. So we think of the particle systems as toy models for a population undergoing natural selection. So we think of the particles as representing individuals in the population, and then they're producing offspring, and we're thinking of the location of a particle as representing the individual's evolutionary fitness. And the killing rule is chosen in such a way that the particles that are killed are the particles with lowest fitness. So only the fittest particles survive. So that's the selection going on. And these models were introduced in the physics literature by Brunet and Derrida in the 1990s. But there are also much more recent results and open conjectures about the long-term behavior of these models. And one of the things that we're particularly interested in, because these are toy models for a population, we're interested in the genealogy or family tree of a sample from the population. So what I mean by that is that we would take some fixed size sample that we would choose uniformly at random from the population at a large time t, and then we would trace the ancestral lineages of that sample backwards in time. And there would be times at which the particles in the sample had a common ancestor, and so their ancestral lineages would coalesce. And so what we end up with is a coalescent process. So this is a sort of cartoon of what the coalescent could look like. So as you go backwards in time, then there'll be a time like this when these two ancestral lineages coalesce because they had a common ancestor at this time. And you sort of keep tracing that back until you have a single common ancestor. And so what we're interested in is, what does this coalescent process look like? In particular, if you fix the size of the sample, but you let the total population size go to infinity, what's the limiting behavior of this genealogy, this coalescent process? So now I want to define for you the particular branching selection system that I'm mostly going to be talking about today, which is the Nparticle branching random walk. So the Nparticle branching random walk is a discrete time branching selection system, and it consists of n particles that have locations on the real line at each integer time step. So we have some real valued random variable that we'll call capital X, and we'll sometimes call that the jump distribution. And then we'll start the process with some whatever initial particle configuration that we want. And then at each time little n in the non-negative integers, each of the n particles in the system is going to have exactly 2 offspring. And each of these 2n offspring particles makes an independent jump on the real line away from the position of its parent. And this jump has the same law as the jump distribution capital X. But then what we do is that only the n rightmost particles out of those 2n offspring particles form the population at time n+1, so the population in the next generation. So the n leftmost particles of the offspring particles are killed, and only the n rightmost survive. So these first two bits here are the branching step of the branching selection system. So each particle branches into two offspring. And then we have this selection step here where only the n rightmost survive. So again, we're thinking of this as a toy model for a population, and we're thinking of the position on the real line as representing evolutionary fitness. So particles which are further to the right have a higher evolutionary fitness, and those are the ones that survive in the selection step. So in the pictures at the bottom, I'm going to show you what this process could look like for n equals 4 for just one single generation of the process. So we'll start with some configuration of the particles on the real line. Each of them has exactly 2 offspring, each of which makes an independent jump away from the location of its parent. And then we see which 4 particles are rightmost. So that's these 4 particles, and these 4 particles are going to get killed. So we kill those particles, and these 4 rightmost particles form the new generation at time n+1. So you can see from this this picture that after you've had the selection step, after particles have been killed, then it's possible that a particle in the previous generation has 0 surviving offspring, like this particle, or it could have exactly 1 surviving offspring, like this particle and this particle, or it could have 2 surviving offspring. So we're going to, our notation is going to be that we'll write x1n of little n, x2n of little n, and so on up to xnn of little n for the ordered particle positions on the real line at time little n.
Sorry, Sarah, I missed the point that at time 0, what is the location of the particles? All are
so you can just pick some initial configuration.
Okay.
Yeah. So it doesn't, yeah. So actually all of our results are going to hold for any initial configuration. That's not going to affect the results.
Thank you.
Yeah. So x1n is going to be of little n will be the position of the leftmost particle, and xnn is the position of the rightmost particle. So we're going to be thinking of capital N as being very large. So what you should have in mind is a large cloud of particles that's gradually moving to the right along the real line. So there are sort of 2 main properties that we're really interested in for this particle system. So the first is the asymptotic speed at which the cloud of particles moves to the right. And then the second is what I talked about before, that we're interested in the behavior of the genealogies. So I want to start by telling you about what's known and conjectured in the case where the jump distribution is light-tailed, or in other words, when it has finite exponential moments. So first of all, for the asymptotic speed at which the cloud of particles moves to the right. So first of all, it's actually not too hard to show that if the jump distribution capital X has finite mean, then there exists a deterministic Vn, which is strictly positive and finite, such that if you take the position of the rightmost particle at time little n, so xnn of little n, and you divide by little n, that converges almost surely and in L1 as little n goes to infinity to this V capital N. But also if you replace xnn by x1n, then you actually get the same limit. And this can be shown just using Kinguin's subadditive ergodic theorem. So there is an asymptotic speed at which the cloud of particles moves to the right, which depends on the number of particles, capital N. So what Bérard and P showed is they determined the asymptotics of V capital N as capital N goes to infinity, so as the total number of particles goes to infinity. So what they showed is that if the expectation of e to the lambda x is finite for some positive lambda, and also some technical assumptions, some extra technical assumptions on the jump distribution x, which I'm not going to go into, then they showed that V capital N converges to a constant V infinity as n goes to infinity. And then they also showed the asymptotics for how quickly it converges. So they showed that V infinity minus Vn goes like some positive constant c times log n to the -1 as n goes to infinity. So this is saying that the asymptotic speed converges as the number of particles goes to infinity, but it converges extremely slowly because capital N needs to be really huge for log n to the -2 to be very small. And this was actually first conjectured by Brunet and Derrida in 97. And there's a related result for the Fisher KPP equation with noise that turns out to be a closely related model. And that was proved by Miller, Mitnick, and Castell. So that's what's known for the asymptotic speed. Then how about the genealogy? So what precisely do I mean by the genealogy? Well, I mean that we take a fixed number k and we sample k particles uniformly at random from the n particles in the system at a large time. And then we trace their ancestry backwards in time, giving us a coalescent process in which ancestral lineages coalesce when they have common ancestors. So there's a conjecture that's due to Brunet, Derrida, Muller, and Meunier, which says that if the jump distribution is light-tailed, then if you look at the genealogy of a sample and you look at it on a log n cubed timescale, then it converges to a Boltzhausen-Snitman coalescent as the number of particles n goes to infinity. So I want to show you a picture of what a Boltzhausen-Snitman coalescent looks like. So actually on the left is a different coalescent, the Kinguin coalescent, which is perhaps the most famous coalescent. So in the Kinguin coalescent, you start with all your ancestral lineages, and then each pair of ancestral lineages independently merges after an exponentially distributed time with rate 1. And you only get pairwise mergers, so you only ever have 2 lineages merging at any one time. And so it ends up looking something like this. So these simulations are thanks to Gertz Kersting and Anton Bacholbinger. And Kinguin's coalescent is what you tend to get in a neutral population. So in particular, it's what you would get if you changed the definition of the n-particle branching random walk to say that instead of killing particles based on their position on the real line, if in each generation you just chose n particles to kill uniformly at random from the offspring particles, then if you did a suitable time rescaling of the genealogy, what you would get is a Kinguin coalescent. But what you're conjectured to get instead, if you define the n-particle branching random walk as I described, and if the jump distribution x is light-tailed, then you're conjectured to get a Boltzhausen-Snitman coalescent, which looks like this. So you can see that it looks very different, mostly because you can have multiple merger events in which lots of ancestral lineages, like here, all simultaneously coalesce into a single ancestral lineage. And the Boltzhausen-Snitman coalescent is conjectured to be the scaling limit of a large class of models of populations under selection, but it's only been proved in a few very special cases. So there are results by very sticky in Schweinsberg and also by Schweinsberg about this, but this conjecture hasn't been proved for the n-particle branching random walk. So that's just a bit about what the coalescents look like. Now I'll go back to the results about the n-particle branching random walk with light-tailed jump distribution. So just to remind you, we had this result about the asymptotic speed and then a conjecture about the genealogy. So actually what I'm mostly going to be talking about today is the case where the jump distribution is heavy-tailed, and it's going to turn out that that these two properties are very different in the heavy-tailed case to the light-tailed case. So now I want to start telling you a bit about the heavy-tailed case. So what do I mean by a heavy-tailed jump distribution? Well, to start with, I'm just going to take a very simple example, and we'll have slightly weaker assumptions later on. But for now, let's suppose that the probability that capital X is bigger than little x goes like x to the minus alpha as x goes to infinity for some fixed positive alpha. So we'll actually weaken this later on to saying that this is just a regularly varying function, but for now, let's stick with this. So first of all, what's known about the asymptotic speed at which the cloud of particles moves to the right? So this is a result of Bérard and Maillard from 2014. So they say that if the jump distribution has finite mean, So we already know that in that case, if you look at the position of the rightmost particle at time little n and divide by little n, that converges almost surely and in L1 to some V capital N. But what Bérard and Maillard showed is what are the asymptotics of V capital N as capital N goes to infinity. So they showed that that V capital N goes like some constant C alpha that depends on alpha times n to the 1 over alpha times log n to the 1 over alpha minus 1. So in particular, as capital N goes to infinity, then this V capital N actually goes to infinity as well. So the asymptotic speed goes to infinity as the total number of particles goes to infinity. And they also showed that if the mean of the jump distribution is infinite, then the cloud of particles actually accelerates. There is no asymptotic speed, and they showed what the cloud of some things about the long-term behavior of the cloud of particles moving to the right in that case. So I've sort of, by having this assumption up here, I've actually showed a slightly weaker version of their results. So what they prove is actually under slightly weaker assumptions on capital X, but that gives them a slightly more complicated form for Vn. So I've just showed you this sort of simplified version of their result. So that's the asymptotic speed. What they also show is what they don't show is the behavior of the genealogy. But what they conjectured is that the genealogy of a sample of particles on a log n timescale is approximately given by a star-shaped coalescent when capital N is very large. So this is a different timescale to what's conjectured in the light-tailed case. So in the light-tailed case, it's conjectured to be a log n cubed timescale. And what I mean by a star-shaped coalescent is a coalescent in which all the ancestral lineages, none of them merge until one single time where all of the lineages instantaneously merge into a single ancestral lineage. So our main result is proving this conjecture of Bérard and Maillard about the genealogy. So before I show you our main result, I just want to give...
Sorry, Sarah, to interrupt. One thing, so here the Vn depends on the distribution of the random jump distribution, is it?
Yes, yes.
But not in the light-tailed case.
So in the light-tailed case, it does as well, yes.
Okay, okay.
Yep, yeah, in all cases. So I've sort of hidden the dependence on the jump distribution, but yeah. Thanks. So you fix your jump distribution and then you vary the number of particles n, and so Vn varies depending on the number of particles n, but you're always fixing your jump distribution.
Okay.
Okay, so I'll show you the conditions for our main result. So we're going to assume that the probability that our jump distribution capital X is bigger than X is equal to, well, we'll define h of X so that this is equal to 1 over h of X for non-negative X. And we're going to assume that h is a regularly varying function with some positive index alpha. So what I mean by that is that for any positive y, if you take h of X times y and divide by h of X, and you let X go to infinity, then this converges to y to the power of alpha. So in particular, you could think of the special case where h of X is equal to X to the power of alpha for X greater than or equal to 1. And we're also going to assume that the probability that X is non-negative is equal to 1. So we're assuming that there are no negative jumps made by particles. And this assumption was also made by Bérard and Maillard and Bérard and Gouret in their work. And so it does make the proofs easier, but we also believe that it doesn't actually make any difference to the behavior. It just simplifies the proofs somewhat. And then we're going to define Ln to be the ceiling function of log base 2 of n. So this turns out to be the relevant timescale for looking at the process. And one way to see that it might be a relevant timescale is that in time Ln, it's possible for a single particle to grow a tribe of 2 to the power of ln descendants. Because if none of its descendants are killed in any selection step, then in a time t, it will have 2 to the power of t descendants. And because 2 to the power of ln is greater than or equal to n, that means that in time ln, the descendants of a single particle can take over the whole population. And this turns out to be why it's the suitable timescale for looking at the process. And then actually what turns out to be the suitable space scale for looking at the process is to let an be h inverse of 2n times ln. So this is where h inverse of x is the generalized inverse of x, so it's the infimum of y, such that h of y is bigger than x. So you can see from the definition of h that h is non-decreasing. So why is this the relevant space scale? Well, one way to see that it might be is, let's take a positive constant c1 and another positive constant c2. So then what's the number of jumps that you would expect to see in the Nparticle branching random walk? The expected number of jumps that are of size bigger than c1 times an during a time interval of length c2 times ln. Well, the expected number of jumps is going to be the total number of jumps during that time interval, which is, well, at each time step you have 2n jumps because there are 2n offspring particles that all jump. And then the time interval is of length c2 times ln. And then we need to multiply by the probability that a single jump is bigger than c1 times an. So by our definition of h up here, we can write this probability as 1 over h of c1 an. And then because h is regularly varying, we can, if we're going to let n go to infinity, we can take this c1 out the front and put it to the power of alpha. And then h of an, by the definition of an here, h of an is going to go like 2n ln as n goes to infinity. So on the bottom here, we can put c1 to the alpha times 2n ln. But then this 2n ln cancels from the top and the bottom. And so we get a limit of c2 over c1 to the alpha as n goes to infinity. So in particular, this is finite and positive. So we're saying that the expected number of jumps that you'll see that are of size order an during a time interval of length order ln is a positive constant. So so this suggests that this space scale is the space scale of which you see the largest jumps happening during this time scale. And it turns out to be the right space scale for looking at the process. So those are our conditions and our a couple of definitions here. So now I want to give you our main result. So it's a slightly wordy version of what is a rigorous result to try and make it easier to digest. So when I say here with high probability, what I mean by it is with probability converging to 1 as capital N goes to infinity. So what we show is, so if you take a small positive eta and you take an integer k and you take a time t that is bigger than 4 times ln, then the following happens with high probability. So first of all, we can say something about the spatial distribution of the cloud of particles. So we can say that with high probability at time t, there are n minus little o of n particles in the space interval x1n of t up to x1n of t plus eta times an. So there are n particles in total, so this is almost all of the particles, and this is the position of the leftmost particle at time t. So, and because we can take eta as small as we like, we're saying that on this an space scale, almost all of the particles are very close to the leftmost particle. And then the other thing that we prove is about the genealogy. So we show that the genealogy on an ln timescale is asymptotically given by a star-shaped coalescence. So more precisely, what we say is that there's a random time capital T that's between little t minus 2 ln and t minus ln, such that if you now take a uniform sample from the population, then with high probability, if your uniform sample of size k is taken from the population at time t, then every particle in the sample is descended from a single particle at time capital T, which is actually the rightmost particle in the population at time capital T. And also no pair of particles in the sample has a common ancestor after time capital T plus epsilon n times ln. And this is for any sequence epsilon n that goes to 0 as n goes to infinity, but such that epsilon n times ln goes to infinity as n goes to infinity. So we're saying that every particle is descended from a single particle if you go back to time capital T, but if you go back to time capital T plus something that is quite large, but it's little o of ln, then no pair of ancestral lineages has coalesced by that point. So I want to show you a picture to illustrate this genealogy result, because I think it's a bit easy to understand with a picture. So at the bottom of the slide, I'm showing you just the same thing that I said before for the genealogy result. So then what the picture is trying to show is, so if you had k equals 6 and you sample your 6 particles at time t, so then this is tracing their ancestral lineages backwards in time until time capital T, and little t minus capital T is between ln and 2ln. And then we've got this time capital T plus epsilon n times ln. So this difference in time is little o of ln, and this difference in time is order of ln. And what you can see in the picture is that ancestral lineages are, none of them have coalesced until you get back to this time. And between this time and time capital T, then all the coalescence happens to get you to a single ancestral lineage, but it all happens pairwise. So there's only ever a pair of lineages that coalesce together, not multiple lineages. And this is what happens in the actual process, because ancestral lineages only coalesce if 2 particles had a common ancestor, but each particle can only have at most 2 offspring in the next generation. So you can only ever have two ancestral lineages merging at a time. So you can see that what the result is saying is that even though all the coalescence is actually pairwise, with high probability, all of the coalescence happens within a really short amount of time on the ln timescale. And so when you look at the coalescent process on the ln timescale, then it looks as if all of the coalescence happens instantaneously. And so what you see is a star-shaped coalescence. So that's our main result. And in the second talk, I'm going to try and give you a sort of sketch proof of the main ideas in the proof of the main result. But what I want to do now is give a couple more results that we proved in similar ways that put our main result in context a bit. So first of all, there's a sort of second result about this spatial distribution of particles. So at the top, I'm reminding you of what our main result said, which was that at time t, there are n minus little o of n particles in the space interval from x1n of t up to x1n of t plus eta times an with high probability. And for this, you could choose your eta to be a very small positive constant. So what we can actually show, so I said that it seemed plausible that an was a good space scale for looking at the process on, because you see order of 1 jumps of size order an during a time of order ln. But it turns out that it really is the right space scale for looking at the process on, in the sense that the diameter of the cloud of particles is of order an. So what we can show is that for any positive r, there exists PR less than or equal to QR strictly between 0 and 1, such that QR goes to 0 as r goes to infinity, and PR goes to 1 as r goes to 0. And such that for a positive r, if you take n sufficiently large and you take time t large enough, then the probability that the difference between xnn of t and x1n of t is at least r times an, that probability is between PR and QR. So this is the position of the rightmost particle at time t. This is the position of the leftmost particle. So this is the diameter of the cloud of particles at time t. So if we think of, first of all, of R being extremely large, then we know that QR would be very small. And so this would tell us that the probability that the diameter is at least R times AN would be very small. And then if we think of R being very close to 0, then PR would be very close to 1. And so the probability that the diameter is at least R times AN is very close to 1. So essentially this is saying that the diameter of the cloud of particles is of order AN. So our main result says that almost all of the particles are very close to the leftmost particle on this AN space scale. And then this result says that there are a few outliers that are actually distance order of AN away, but most of the particles are clumped very close to the leftmost particle. And then another result about the genealogy. So again, I'm reminding you of what our main result said. So our main result said that with high probability, there's a random time capital T between T minus 2ln and T minus ln, such that with high probability, if we take a uniform sample of k particles at time t, then every particle is descended from a single particle at time capital T, and no pair of particles has a common ancestor after time capital T plus something that's little o of ln. And what we can show is that this time capital T is genuinely random, and that for any subinterval of this interval that has length of order ln, then there's a positive probability that capital T is in that interval. So a probability that's bounded away from 0 as n goes to infinity. So what we can show is that if you take S1 strictly less than S2 and both between 0 and 1, then there exists a positive P such that for n sufficiently large and for a time t that's bigger than 4 ln, then the probability that this coalescence time capital T is between t minus 2 ln plus S1 ln and t minus 2 ln plus S2 ln, that's bigger than P for n sufficiently large. So really what I'm writing here is a shorthand for the probability that there exists a time capital T in this interval, such that then with high probability, if you take a uniform sample, every particle is descended from a single particle at that time capital T, and no pair of particles has a common ancestor after time capital T plus little o of ln. So that's a couple of results to put our main result in context. So now what I want to do is just sort of summarize the results and conjectures about the genealogies for the Nparticle branching random walk with different jump distributions. So if capital X is our jump distribution, then I said that in the light-tailed case, which you can think of as being roughly the case where the probability that capital X is bigger than little x is less than or equal to e to the minus c times x for some positive constant c. So in that case, it's conjectured that if you take a uniform sample and you trace the ancestry backwards in time, the time until you see coalescence, so the time that you have to go backwards to see a most recent common ancestor, is of order log n cubed, and the coalescent process on that timescale will look like a Boltzhausen-Stepman coalescent. And then I said that in the heavy-tailed case, where the probability that capital X is bigger than little x goes like x to the minus alpha for some fixed positive alpha. So what we proved is that the time to coalescence is of order log n, and if you look at the coalescent process on that timescale, then it looks like a star-shaped coalescent. So another natural question to ask is what happens between these two cases, and probably the most natural jump distribution to take to understand what happens between these two cases might be the stretched exponential distribution. So to have a stretched exponential tail where the probability that capital X is bigger than x goes like e to the minus x to the power of beta for some beta strictly between 0 and 1. So this is actually work in progress with my PhD student Jafia Taigash. So what we want to understand is what the timescale is to coalescence, and maybe an even more ambitious result would be to try and understand what the coalescent process looks like. So what we believe is that there's a critical value of beta at which the timescale for coalescence changes in this regime, but this is still very much work in progress. So to sort of illustrate these three different regimes, I want to show you a quick simulation that was done by my PhD student, Jafia. So I'm just going to, because I'm not technologically advanced enough to embed it in my slides, I'm going to just close my slides and show you a video, if that's going to work. Whoops. Okay, so can you see the? Can you now see the video?
Yes.
Great. So at the top, we've got an Nparticle branching random walk with a heavy-tailed jump distribution. And then in the middle, we've got one with a stretched exponential tail. And at the bottom, we've got one with an exponential, with a light-tailed one. And the circles are particles, and they're making jumps along the real line. So you can see that in the red one at the top, there are some really big jumps like that one that happened there, where eventually its offspring just take over the whole population, and so the sort of worm of the Nparticle branching random walk moves along in a very sort of jumpy way, whereas in the light-tailed case it's a much more gradual motion, and then the stretched exponential case is sort of somewhere in between. So I'll just let that video play a little bit. Okay, so now I'm going to go back to my slides. Can you see my slides again?
Yes.
Yes.
Great, thanks. Okay, so that's all I was going to say in this talk about the Nparticle branching random walk, and I just wanted to end in the last few minutes by mentioning another branching selection system, which has also been studied quite a lot, which is the and it's closely related to the Nparticle branching random walk, and it's an Nparticle branching Brownian motion. So instead of a discrete time process, this is a continuous time process. So it's called the NBBM for short. So the NBBM consists of n particles that are moving around on the real line according to independent Brownian motions. And each particle is also carrying with it a clock that has an independent exponentially distributed amount of time on it with mean 1. And at the end of that time, when the clock rings, then the particle branches into two particles. But each time a particle in the system branches, then the leftmost particle in the system is killed. So there are exactly n particles in the system at all times. So on the right, I'm showing you what this process might look like. So first of all, our particles move according to their independent Brownian motions until one of them decides to branch. So here, this green particle decides to branch. So then what happens, we see which particle is the furthest left. So that's the red one. That particle is killed. And then the green particle branches into two, and all the other particles just continue. And they all move according to Brownian motions until, again, one of them decides to branch. So then again, we see which particle in the system is leftmost. That particle is killed, and the green particle branches into two, and the other particles continue. And what we could have is that the particle that decides to branch could actually be the leftmost particle. So what happens then is that the leftmost particle branches, but then immediately either it or its offspring is killed because they are the leftmost particle. And so effectively no branching happens, and all of the particles continue along. So we always have exactly n particles in the system. So this model was introduced by Pascal Maillard in 2012. So it's a natural continuous time analog of the Nparticle branching random walk and other branching selection systems. And the conjecture, which is due to Brunet and Derrida and also to Pascal Maillard, is that if you take a sample from the NBBM at a large time, and then you look at the genealogy of the sample on a log n cubed timescale, then that is conjectured to converge to a Boltzhausen-Snip uncoalescent as the number of particles n goes to infinity. So it's conjectured to have the same behavior as the light-tailed case is conjectured to have in the n-particle branching random walk. And one possible tool that you have at your disposal for the NBBM that you don't have in the n-particle branching random walk is a hydrodynamic limit result that says that if you look at the process on a fixed timescale and you let the number of particles n go to infinity, then the density of particles converges to a solution of a particular PDE called a free boundary problem. And this is a hydrodynamic limit result that's due to De Masi, Ferrari, Prezzuti, and Soprano-Lotto from 2017. So that is a tool that can be used to understand the NBBM. But in order to make progress towards this conjecture, then what you would need to do is strengthen this result to not just be over a fixed timescale, but to well, first of all, understand the long-term behavior of solutions of this free boundary problem, but then to show that that long-term behavior governed the behavior of the NBBM over long timescales of the timescale of a genealogy, and not just on a fixed timescale. So that's actually all I want to say in the first talk. So in the second talk, I'm going to go back to the n-particle branching random walk and give you the sort of sketch proof of our main result about the genealogy, the star-shaped genealogy for the heavy-tailed case. So I'm going to finish by showing you again this summary slide of behavior for the genealogy for the n-particle branching random walk. So thanks very much for your attention.
Thanks, Sarah. Before you break, any questions of Sarah?
So I have a couple of questions. So one is that the branching Brownian motion results you indicated are analogous to the light-tailed setup in the branching random walk. So what would be analogous for heavy-tailed? Is there some Levy process or something?
Yeah, so I guess you could define an n-particle branching stable symmetric process, I guess, which I would think would have the same behavior as the n-particle branching random walk. So you would need you would just need the increment of a particle over a fixed timescale to then have a heavy-tailed distribution rather than the Gaussian distribution that you get in the branching Brownian motion.
Okay.
Yep.
Thanks. And the x being non-negative, is that is that actually a technical assumption that's present, or is it just for the talk you use that as a simplification?
So we do actually use that in our proofs. So I think we probably could prove the result without that assumption, but the proof is already quite long, and I think that would make it significantly longer. So it sort of shouldn't make any difference, right? Because if you've got a large number of particles and if some of them make negative jumps, then they're just going to be killed pretty quickly anyway. So so for example, I guess you could assume that the jump distribution was bounded below by something, and then the proofs would probably be a little bit more complex, but it wouldn't be too bad. But then I think my feeling is that it's a technical assumption that makes the proof significantly easier, but doesn't actually really change the behavior. So I don't think you would see any more interesting behavior if you took that assumption away. It's just that your proofs would get nastier.
Okay. Thanks.
Yeah, I think we can start now. Yeah, Sarah.
Great. So thanks for coming back for the second talk. So what I'm going to be speaking about now is a sketch proof of our main results, to try and give you some of the main ideas. So I'll just start by recapping the definition of the of the Nparticle branching random walk. So it was a discrete time branching selection system consisting of n particles with locations on the real line at each time step. And we have x, which is a real valued random variable, which is our jump distribution. We start with some arbitrary initial condition of particles, whatever you want to set as your initial condition. And then at each time n in the non-negative integers, each particle has exactly 2 offspring. Each of the 2n offspring particles makes an independent jump away from the location of its parent with the same law as x, the jump distribution. And then only the n rightmost particles of the 2n offspring particles survive to form the population in the next generation at time n+1. So in the pictures, this could be a particle configuration at some time. So first of all, each particle has 2 offspring, each of which makes an independent jump from its parent's location. Then we see which n particles, so here n equals 4, which n particles are the n rightmost. We kill the n leftmost particles, and the n rightmost particles form the population at time n+1. And we're writing x1 n of little n up to xn n of little n for the ordered particle positions on the real line at time n. So this is the rightmost particle position, and this is the leftmost particle position. And then to remind you of the conditions for our main result, so we define a function h such that the probability that the jump distribution capital X is bigger than little x is given by 1 over h of x for non-negative x. We assume that h is regularly varying with some positive index alpha, which means that for any positive y, if you take h of x times y and divide by h of x, that converges to y to the alpha as x goes to infinity. And we also assume that there are no negative jumps, so we assume that the jump distribution is non-negative or Maillard. We also define this timescale and space scale, so Ln is the ceiling function of log base 2n, which turns out to be the right timescale for looking at our process on. And we let an be h inverse of 2n ln, where h inverse is this generalized inverse of h, and this turns out to be the right space scale for looking at the process on. So now I'll just recap the main results that I'm going to talk about the proof of. So our main result, so with high probability meant with probability converging to 1 as n goes to infinity. And our main result says that if you take a small positive eta, you take an integer k and a time t bigger than 4 ln, then with high probability, first of all, at time t, almost all of the particles are in this space interval from the position of the leftmost particle at time t up to the position of the leftmost particle at time t plus eta times an. So they're very close to the position of the leftmost particle on the an timescale, because you can take eta to be very small. And then for the genealogy, we said that the genealogy on an ln timescale is asymptotically given by a star-shaped coalescent. And more precisely, what we show is that there's a random time capital T between t minus 2 ln and t minus ln, such that with high probability, if you take a uniform sample of k particles at time t, then every particle in that sample is descended from the rightmost particle in the population at time capital T, so they're all descended from a single particle, and no pair of particles in the sample has a common ancestor after time t plus epsilon n times ln for any sequence epsilon n that's going to 0 as n goes to infinity, with epsilon n times ln going to infinity. So this is the result that I'm going to try and give you a sketch proof of. So first of all, I want to start with an easy lemma that we're going to prove that will be useful later on. And this lemma relies on the fact that we're assuming that there are no negative jumps. So first of all, let's recall that Ln is the ceiling function of log base 2n, and that x1 n of t up to xn n of t are the ordered particle positions on the real line at time t. So what the lemma says is that if you take a non-negative integer s, then x1 n of s plus ln is at least xn n of s. So in other words, the leftmost particle at time s plus ln is at least at the position of the rightmost particle at this earlier time s. So how do we show this? Well, one way to show it is a proof by contradiction. So let's suppose, aiming for a contradiction, that x1n of t is strictly less than xnn of s for all integer times t between s and s plus ln. So this is supposing that the position of the leftmost particle at all these times t is always strictly to the left of the position of the rightmost particle at time s. So then what would happen then? Well, because all of our jumps are non-negative, that's the assumption that we're making, then what happens to descendants of the rightmost particle at time s? Well, they're always going to be to the right of, or they're always going to be at position at least xnn of s. This is the position of the rightmost particle at time s, because all of the jumps that they make are non-negative. And particles at a time t are only killed if they're to the left of x1n of t. They're only killed if they're to the left of the leftmost surviving particle. And all of these descendants are to the right of this, so they're definitely to the right of x1n of t because of our assumption here. So that means that none of them are ever going to be killed. And so that means that this rightmost particle at time s has 2 to the power of ln descendants at time s plus ln, because none of its descendants are killed. But by our definition of ln, 2 to the power of ln is at least n. So that means that actually all of the particles in the population are descended from the rightmost particle at time s. And that means that because all of the jumps are non-negative, that means that the leftmost particle in the population at time s plus ln must be at position at least xnn of s, because it's descended from a particle at this position. But then that's a contradiction, because it contradicts this assumption up here with t equals s plus ln. So that means that this assumption has to be false, and so there has to exist a time s star between s and s plus ln, such that x1n of s star is at least xnn of s. But now we're done, because all jumps are non-negative. That means that the position of the leftmost particle at a later time s plus ln is at least the position of the leftmost particle at the earlier time s star. So in particular, x1n of s plus ln is at least this, which is at least xnn of s. So we've got this is at least this, which is the result that we wanted. So that's an easy result to show, but it's going to be useful to us later on. So then the second thing that we're going to use is that we can construct our n-particle branching random walk in a natural way from n independent branching random walks. So what do I mean by a branching random walk in this context? I mean that we'll have an initial particle at some fixed position x on the real line at time 0. And then at each time n in the non-negative integers, each time n particle has exactly 2 offspring, each of which makes an independent jump from its parent's location with the same distribution as the jump distribution capital X that we have for the n-particle branching random walk. And then the time n plus 1 particles are just these offspring particles. So I'm just trying to emphasize here that no particles are killed. The offspring all survive to time n plus 1. So that means that the number of time t particles in our branching random walk is exactly 2 to the power of t. So now how do we construct our n-particle branching random walk from these branching random walks? So let's suppose that we want initial particle locations x1 up to xn for our n-particle branching random walk. So then what we do is we take n independent branching random walks with different initial particles, so with initial particles at x1 up to xn. And then what we're going to do is we're going to color the particles in these branching random walks either blue or red. So first of all the particles at time 0 are going to be blue. So we start off with n blue particles. And then we're going to color the particles in an inductive way. So for each non-negative integer n, the capital N rightmost offspring particles of time little n blue particles are colored blue. And all other time n plus 1 particles are colored red. So in particular, all the offspring of red particles are colored red. And for the offspring of blue particles, only the n rightmost are colored blue and the others are colored red. So then the blue particles form an n-particle branching random walk. And that's because at all times we have exactly n blue particles, and for the next generation, they all have offspring that make an independent jump with distribution given by x. And then of those 2n offspring, it's only the n rightmost which stay blue and the others are turned red. So we've got this n-particle branching random walk inside these n branching random walks. And the feature of this construction that's useful is that if you have an ancestor and a descendant in your n-particle branching random walk, then you have some path of jumps that was made to get from the position of the ancestor to the position of the descendant. And that ancestor and descendant in the n-particle branching random walk will correspond to an ancestor and a descendant in one of the branching random walks. And the path of jumps between them will be the same as a path of jumps between that ancestor and that descendant in a branching random walk. And then what's useful is that that path in the branching random walk is actually a random walk. So that's not actually the case in the n-particle branching random walk because you've got all the killing, but in the branching random walk, it genuinely is a random walk. And so that means that if you want to show that something is very unlikely to happen in the n-particle branching random walk for any path between an ancestor and a descendant, then one thing you can do is show that that's very unlikely for a random walk, and then use a union bound to show that it's therefore very unlikely to happen for any path in one of these branching random walks. And then you can use this to say that, well, if it doesn't happen for any path in any of the branching random walks, then it can't happen in the n-particle branching random walk. So that's what we're going to use. And the property that we're going to use that is unlikely to happen in a random walk with heavy-tailed jump distribution is this one. So let's set up our random walk with heavy-tailed jump distribution. So we're going to say that as before, the probability that capital X is bigger than X is given by 1 over h of x, where h is regularly varying with some positive index alpha. And then x1, x2, x3, and so on are going to be IID random variables with distribution equal to x. So then roughly what the property is of this random walk. So I'll give a precise statement in a second, but this is roughly what it says, which is that if you fix a very small positive c, then if you take x to be very large, then it's very unlikely that you sum up xk from k equals 1 to n, and that sum is at least x, but none of the individual xk's are greater than c times x for all k less than or equal to n. So this is just the position of the, you can think of this as the position of a random walk after n steps. So we're saying it's very unlikely that the random walk moves more than distance x in n steps, but none of the individual jumps are, all of the individual jumps are smaller than a small constant times x. And of course, this depends, so you have to have a suitable x and a suitable n. So now I'll show you a more precise result, which is what we use. And this is sort of based on earlier results of Direct and also Gantet. So Gantet's result is for a stretched exponential tail, but we used some elements from Gantet's proof to get a result that was what we wanted to use. So let's take a positive integer m and a positive q and a positive lambda. And then we'll take an r that is strictly between 0 and 1. And it also has to be less than something that depends on lambda, alpha, and q. And then what we can say is that if n is sufficiently large, then if xn is bigger than n to the lambda, so it grows like a positive power of n, then if we look at the probability that the sum from j equals 1 up to mln of xj times the indicator that xj is less than or equal to rxn, the probability that that sum is at least xn is at most n to the minus q. So what this is saying is, let's look at the the distance that the random walk moves in time m times ln, but we're going to set any jump to 0 if it's bigger than r times xn. And so if you remove all the jumps that are bigger than r times xn, then this is saying that it's very unlikely that the random walk manages to move a distance xn. Or in other words, so in particular, you can say that the probability that the random walk manages to move a distance xn and all of the jumps are at most r times xn, that probability is very small. So we can take this q to be as large as we want, and it's just that by taking q to be large, we get this more of a restriction on r, because r needs to be smaller. So I'll show you roughly how we prove this result. So I'll just move the result to the top of the slide, and then this is roughly how we prove it. So first of all, we take a constant c that is between 2q times log 2 and lambda times the minimum of 1 and alpha log 2 over r. So our choice of r here in particular means that such a c exists. And we're going to use Markov's inequality. So the probability that we want, so the probability that this sum is at least xn, what we're going to do is take an exponential of both sides. So we're going to say it's the same as the probability that e to the power of c ln xn inverse times this thing, so times the sum of xj times the indicator that xj is at most r xn is greater than or equal to, and then we on the other side we need to say e to the power of c times ln times xn inverse times xn, so we end up with e to the power of c ln. And because ln is log base 2 of n, or it's within 1 of log base 2 of n, we can basically write this as n to the power of c over log 2. So now we're going to use Markov's inequality to say that this is at most n to the minus c log 2 times the expectation of this thing. Because all of the xj's are IOD, we can write the expectation of this as the expectation of e to the c ln xn inverse x times the indicator that x is at most r times ln, and then to the power of m ln, because we've got m ln terms in our sum. So all we need to do now is estimate this expectation. And the way that we estimate this expectation is using a nice identity, which is in this paper of Gantert. So it's a nice identity for estimating the a sort of truncated exponential moment. So the identity says that the expectation of e to the vy times the indicator that y is less than or equal to some positive k2 times the indicator that y is at least some smaller constant k1. That can be given by an integral from k1 up to k2 of an integrand times the probability that y is bigger than u du, and then plus a couple more terms. So all of these terms only depend on the tail probabilities of this random variable y. And so this makes it very nice for us to use, because our assumptions are about the behavior of the tail probabilities for x, saying that that's given by 1 over a regularly varying function. And so just that assumption and using this identity allows us to show, using the assumption on C here, and because ln is much smaller than xn, so using this assumption on xn up here, it lets us show that the expectation that we want to bound is 1 plus something that's of order n to the minus epsilon for a positive constant epsilon. And so that means that when we plug it back into here and we put it to the power of m times ln is log n. So so even to that power, it's just going to be an order of 1 term. And then because c over log 2 is bigger than 2q, we've got n to the minus 2q times something that's of order 1. And that gives us the result that we want when n is large. So that's roughly how we prove this result. So then how are we going to use this result? So what we do is use it with xn being a constant times an. So an was our space scale. It was given by h inverse of 2n times ln. So if we think of h of x as roughly being x to the power of alpha, then we should think of an as essentially being 2n ln to the power of 1 over alpha. So it's going to satisfy this condition here that it's that then xn will be bigger than n to some positive power. So what we're going to do in the proof is we're going to fix a small constant rho, which will be positive but very small. And then in our Nparticle branching random walk, we'll say that a jump that is larger than rho times an is a big jump. And then if we take a small positive constant c, which is small but still much bigger than rho, then if rho is small enough, if we fixed rho to be small enough compared to c, then we can see that it's actually very unlikely that there is a time t particle in our Nparticle branching random walk that has moved more than distance c times an away from its ancestor at a time order of ln earlier, unless there was an ancestor between its ancestor and the particle itself that made a big jump. So the reason that we can see this is that if we take rho small enough, then we can say that the probability that a random walk moves more than c times an without making a big jump, we can say that that probability is at most n to the minus 1,000 using this lemma. And that means that we can say that the probability that there is such a random walk inside one of our branching random walks that we use to construct the Nparticle branching random walk, the probability that there is such a path in one of those branching random walks is also extremely small, just using a union bound. And so we can then say from that that it's very unlikely that this happens at all in our Nparticle branching random walk. And so the only way that a particle can move, or a sequence of descendant particles can move more than a distance, a small constant times an, the only way that it can do that is by having making at least one big jump. And what's the probability that a jump is a big jump? Well, it's the probability that our jump distribution x is bigger than rho times an, which is 1 over h of rho times an. And because h is regularly varying, we can take this rho out the front and put it to the power of alpha. And then h of an from this definition here is essentially 2n times ln. So this goes like rho to the minus alpha times 2n ln to the minus 1. So what rate do we see big jumps in our process? Well, at each time step in our process, we have 2n jumps that happen. And so the rate that we will see big jumps happening is of order ln to the minus 1. So that's going to be useful as well. So what I'm going to do now is try and give you a sort of heuristic sketch proof of our result based on a picture. So this is the picture. So we're going to let time t1 be time little t minus ln, where ln was the ceiling function of log base 2n. And we're going to let time capital T be the last time before time t1 when a particle makes a jump that's bigger than rho times an, so when a particle makes a big jump, and that particle takes the lead. So what I mean by that is that that particle makes a jump away from its parent and it becomes the rightmost particle in the new generation. So what we're aiming to show is that this capital T is actually the time that we want. So we want to show that at time little t, almost all the particles are descended from this single particle that makes this big jump and takes the lead at time capital T. So in this picture, time is going up the slide and the particles are being shown sort of left to right at different times. So this is time little t, and then this is going back to time capital T, which is sometime before this time t1. So I'm going to try and explain what is happening in this picture, which is sort of meant to be showing what happens with high probability in the process between these times. So first of all, what's happening in step A, so these arrows are meant to show big jumps that are happening at those times. So A is saying that a particle, so by the definition of the time capital T, a particle makes a big jump at that time and it takes the lead. And it's very likely that it takes the lead by a distance of order an, because it's making a big jump of size order an. So it's very unlikely that it makes this big jump but lands really, really close to another particle. So we can assume that with high probability, it's now ahead by a distance of order an. And its descendants are going to stay in the lead until time t1 with high probability, in the sense that other particles that are not descended from this particle are not going to overtake it by time t1. And that's because the definition of the time capital T says that there's not allowed to be another time later before time t1 when another particle takes the lead with a big jump. And particles with high probability, we said that they can't move far on the an space scale without making a big jump. And we're saying that this particle takes the lead by a distance of order an. So other particles can't catch up unless they make big jumps. They're not allowed to overtake with a big jump. So the only way they could overtake would be to make a big jump that ended very close to the lead and then overtake with some little jumps. But that requires a big jump to land in a very small interval, and that's also unlikely. So it's very likely that the descendants of this particle stay in the lead until at least time t1. And then what I'm showing in B is that after time t1, then there may be big jumps which do overtake the descendants of this particle. That's quite likely to happen. So like this big jump here could be getting ahead, but there will only be order of 1 big jumps in this time interval, because this time interval has length ln, and we said that the rate at which big jumps happen is order of 1 over ln. So there'll be order of 1 of these big jumps, and it's very unlikely that any of them will happen right after time t1. There'll be a time of order ln after time t1. And so they've got significantly less time than ln to build descendants by time t. And because you can only build 2 to the t descendants in time, 2 to the s descendants in time s, that means that they'll have much fewer than n descendants at time t. So they'll be growing a tribe of descendants like this particle here, but they'll have much fewer than n descendants by time t. And because there are only order of 1 of these big jumps, and each of them has little o of n descendants, then in total they'll only have little o of n descendants. So it's only going to be a small number of a small amount of the total population that will be these particles that overtook this tribe descended from this particle. And actually, the only way that particles can overtake this tribe is by making big jumps, for the same reason that I said before, that you can't move very far without making big jumps. So that means that actually by time t, then n minus little o of n of the particles will be in this tribe descended from this particle. So what C is showing you, it's a sort of zoom in of the descendants of this single particle that made this big jump. So it's saying that the tribe descended from the time t leader from this particle, it doubles in size at each time step up to almost time t plus ln. And that's because there are only little o of n particles that get ahead of this tribe. And so until the tribe itself has reached nearly size capital N, then none of the offspring of the tribe will ever get killed, because they won't be the leftmost particles. So that will happen until almost time capital T plus ln, when the tribe will have size getting close to n. And then what D is showing is that actually from time t plus ln onwards, then so this blown up bit is showing that actually some of the particles of the tribe will now get killed in the selection steps, because they will be among the n leftmost offspring particles. But because what we said before is that there are only little o of n particles that have got ahead, then during the time interval from t plus ln up to little t, the time t leader's tribe still has size n minus little o of n. It's just not growing anymore. So that's roughly what happens between these times capital T up to little t. And in particular, what we've said is that because the size of this the size of the number of descendants of this single particle is n minus little o of n, that means that almost all of the particles at time little t are descended from this single particle, which is one of the things we wanted. So then another thing that we wanted, that we claimed in the main result, was that the time capital T is between t minus 2 ln and t minus ln, or in other words, it's between t1 minus ln and t1 with high probability. So by the definition, it's always got to be at most t1, but in order to show this, then you have to convince yourself that there is a time between these two times when a particle takes the lead by making a big jump. So what could go wrong? So what happens if no particle manages to take the lead with a big jump during some time interval that has length ln? So during some time interval from s up to s plus ln for some s. So now we can use our warm-up lemma, which says that x1n of s plus ln is always at least xnn of s. So the position of the leftmost particle a time ln later is always at least the position of the rightmost particle. And what that means, so if we use this and the assumption that no particle takes the lead with a big jump, what that means is that if we look at the diameter of the cloud of particles at time s plus ln, and we divide by an, so we know that this term, the position of the leftmost particle, is at least xnn of s. And then because no particles have taken the lead with a big jump, that means that the position of the rightmost particle at this time, it can't have moved very far from the position of the rightmost particle at the start of the time interval at xnn of s. So actually this also has to be close to xnn of s, because if you haven't made any big jumps, you can't have moved very far. So that means that this, if you divide by an, that's small with high probability. And then if the diameter is small on the an space scale, that means that it's easy for a particle to take the lead with a big jump soon afterwards, because anywhere that it is in the cloud of particles, as long as it makes a fairly big jump, it will actually take the lead. So that then means that it's very likely that a particle will take the lead with a big jump soon after this time interval. So it's likely to happen within a time interval of length 1 plus delta times ln. So what we want to show is that it will happen within a time interval of length just ln. So we will have to work a little bit harder to do that, but you can use this kind of idea to show that if nothing takes the lead with a big jump, the diameter ends up being really small, and that ends up meaning that it's easy to take the lead with a big jump. So that's roughly how we show this. And then another thing that we wanted to show was the result about the spatial distribution of particles. So I claimed that n minus little o of n particles are close to the leftmost particle at time t on this space scale of an. And so this is not too hard to show once you've got this whole picture sorted out, because so first of all, there are only little o of n particles that are not in this tribe at time t. So there are these sort of outlier particles, but you know that there are only little o of n of those. So you can ignore those particles and just worry about the particles descended from this particle. And then it's not too hard to see that there are no big jumps made by particles in this tribe descended from this particle up to time t plus ln. And that's because big jumps happen at rate 1 over ln if you're allowing big jumps to come from any of the n particles. But this tribe will have, up to this time, this tribe will be much smaller than size n. And so big jumps will happen much more slowly. And so you actually won't see any big jumps with high probability. And this time, because of what we showed it, that t must be more than t1 minus ln, then this time ends up being more than t1. So there are no big jumps made until this time. And then from time t plus ln up to t, there are only order of 1 big jumps. And each of those big jumps will only have little o of n descendants because it's got less than time ln to grow descendants. So that means that there are actually only little o of n particles in this tribe that have a big jump in their ancestry between time little t and capital T. So again, we can ignore those particles, and we're still left with n minus little o of n of particles, all of which are descended from this particle, and all of which don't have a big jump in their ancestry between these times. And you can't move far on the AN space scale without making a big jump. So that's enough to get this result. And then the final thing that that we claimed was that the genealogy is star-shaped. So we claimed that if you trace ancestry of a sample back to time a little bit after time capital T, then none of the ancestral lineages have coalesced. And that follows if you can show that with high probability, none of the particles at time T plus epsilon n ln, which was the time that we had for wanting to show that no lineages have coalesced by that time. So you want to show that no particles at this time have order of n time t descendants. Because if you can show that, then if you take a fixed number of particles at time t, it's very unlikely that you have any pair that's in the same, that's descended from the same particle at this time. So how do we show this? Well, first of all, you can say that no particles at this time have order of n time t descendants if they're not in the tribe descended from this particle, because there are only little o of n particles in total at this time that aren't descended from this particle. So we can just think about the particles descended from this particle. And then it's not too hard to show that none of the particles in the time t leaders tribe has moved very far by this time t plus epsilon n ln, because it's just a tribe of particles started from a single particle, and it hasn't run for very long because we're taking epsilon n to be small. So none of them have actually moved far on the space scale that turns out to be relevant. And that allows you to show, using concentration inequalities, that actually the descendants are fairly equally shared out between them with high probability. So you can show that each has of order n times 1 over the number of particles that there are, so n times 2 to the minus epsilon ln descendants at time t. And in particular, because in our assumptions for this theorem, we assume that epsilon n times ln goes to infinity as n goes to infinity. So this is little o of n. So no single particle has a large share of the descendants at time little t, and that means that we get the star-shaped behavior for the genealogy that we wanted. So that's sort of all I wanted to say for a sketch proof of the main results. So thanks very much for your attention.
Thanks, Sarah, for the very interesting talks. Should we unmute ourselves and thank the speaker?